Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks to the organizers for organizing this wonderful workshop, and thanks for inviting me as well. So today I'm going to talk, it's an overview talk on what I call component-based models. Now, what are component-based models? Those are graphical models, sparse models, low-rank models, and all of that sort of thing. So it really encompasses a lot of what has happened in the last decade and a half in statistical machine learning. Okay, so before going into what these are, let's look at the setting, the kinds of data for which you need these kinds of models. So the main principal setting of data is that of what is known as high dimensional data. So that is where, so let's look at fMRI images, for instance. Here. So what happens in MRI images is that you go into this huge machine and it gives you images of slices of your brain. So that's 3D images, and that's over time. And so it's a lot and lot of data. And so high dimensional. And another kind of biological data is gene expression data. So there you have tens of thousands of genes. And so if you look at it as number of variables, though they number in the tens of thousands. Now 10,000 doesn't seem like that big a number, right? It's large, all right, but is it high dimensional? So high dimensional has another facet to it, which is that the number of variables swamp the number of observations. So here, if the rows are the number of variables, the genes, the columns are the observations. So each column corresponds to an experiment which costs $100. And so you don't have that many experiments, don't have that many observations. So another prototypical example, increasingly important in recent years, is social networks. So there you have, if you look at Facebook, you have 1 billion nodes. So if each of that is a variable, high dimensional. And if you look at the number of observations you have of jointly of all these variables, you don't have 1 billion measurements. You have measurements of parts of the network, and even those are quite a few. Okay, so this is what we mean by high dimensional. You have many variables in the system, many to the power many, but you don't have that many observations. So this is not that great a setting. What is known as a curse of dimensionality in various guises is that for reliable inference of statistical models, the number of observations that you need, which we will denote here by n, should scale exponentially with the number of variables p. Okay, so n and p are going to be two quantities you should keep in mind. N, the number of observations; p is the size of your model. And the high dimensional setting that we have is that n is much smaller than p, whereas mathematically what we need is the opposite. You need.
Very faint.
Is it? Yeah, it is actually. Right. Okay, I'm sorry for that. I don't know what I can do here, but okay, I'll try to read out more.
How do you make it that faint? It's a tough thing to do.
It's actually not faint, that faint here. I don't know. Of the projector.
Is there any brightness option?
So this is actually gray here. Is this better?
Is this better? Yeah.
No,
I don't think it matters.
So the slides later on are going to get better.
They're going to get brighter.
There'll be more pictures later on. So anyway, so here anyway, there's nothing much on the slides anyway. The key point is really the curse of dimensionality. That's really the point of the slide. And so what can be done? Oops. So classically, when you have too many features, and so this has been actually a setting, even though they say it's a modern setting, this has been a setting in many, many practical settings over the last couple of decades. So, and people have had techniques, heuristics to deal with this. And primarily, it has had to do with the approaches have had to do with dimensionality reduction. You have too many features, reduce the dimensionality, and then you form statistical models over your reduced data. So that has had a lot of success, and it's a reasonable strategy. But over the last decade, what people have realized is that you can have models in situ. You can literally deal with these humongous number of variables and actually form statistical models over all of these without first reducing them and then dealing with all these variables. And primarily, it has been driven by scientific imperatives. So in the earlier example, if I have tens of thousands of genes, then I don't want to form certain random projections of all of those genes. So I really care about statistical models over all of these variables. And so people have really wanted, so that it was always a need that people have had of forming such statistical models. And there are two frameworks that have been really successful. One is graphical models, and another is what I call structurally constrained models. So we will go over these two models briefly in the first part of the talk. So graphical models have two flavors, continuous and discrete, and structurally constrained models are what you must have seen in various guises as sparse models, group sparse, low rank, and so on. Okay, so let's look briefly at graphical models. So here, again, if the words are too faint, you can just look at this graph, which is really the key point. So in graphical models, again, the goal is you have a lot of variables, and you want a joint distribution over all of these variables. So again, if you look at the gene network example, you have tens of thousands of genes, and you want a joint distribution over all of these variables. So this nominally is a very difficult thing to do, right? Because joint distribution is over p variables is a p-variate function. And if you want to learn that from data, it's a difficult thing to do. What graphical models do is that they say, they give you a way of a language to have a compact representation of this p-variate distribution. So here, if I have 5 variables, my joint distribution is a 5-variate function. Right? It has 5 variables. But given this graph, I can write it down in a much simpler fashion. Now, given a graph, you have cliques which are fully connected subcomponents. So here, 1, 2, 3 are fully connected. They have edges between any pair of the variables. An edge is the simplest fully connected non-trivial component. Even a node, you can think vacuously as fully connected. So now, if given a graph, or more importantly, if you give me these subsets of variables, then what a graphical model is just a product of functions which only depend on these subsets of variables. So this is an algebraic way of thinking of graphical models. So instead of a p-variate function, I have a function which only depends on a subset of variables. And that simplifies my storage costs. For instance, even if these variables are binary, so 1, 2, 3, 4, 5, all of these are binary, if I have to store the distribution over 5 variables, the storage cost would be 2 to the 5, because you have that many configurations of variables. Right? But if I have this setting where I have to only store tables over subsets of variables, then my storage complexity will only be exponential in the maximum clique size, here which is 3. Right? It'll scale with the maximum clique size. So in some sense, this is a way to store things more compactly. Your joint distribution is stored more compactly. And going forward, the way that will be useful to think about these graphical models is just that there are 2 components. One, there is a graph, right? You have edges between nodes. And the other, you have weights over cliques of variables. And if it will help, just think of weights over edges. So you have graphs, you have a graph, and you have weights over edges. That is a graphical model. Okay, so let's look at one example. This is an example that comes up a lot, and that's the US Senate example. So this is a social network where you can think of this as Facebook for power brokers, which is a US Senate. So you have, each node is a US senator, and what you are interested in is the social network among these senators. And so if I want to infer such a social network, I need observations. And observations in this setting are their voting records. Each senator votes on a bill, yes or no, or maybe they're absent, but let's imagine that they vote yes or no. And for each bill, you have these yes or no votes across senators, and this is a joint observation of all these senators. And given such multiple joint observations, you can learn a joint distribution over all these US senators. That is what graphical models give you. But in many settings, you're not really interested in the joint distribution, especially if I'm just interested in the social network connecting these senators. All I'm interested in is a graph. I just want to know what is the underlying graph from which you can describe perhaps a statistical model, but just give me the edges. And so here, for instance, from those voting records, you can infer edges between different US senators. So these nodes are blue, these nodes are red, and you can see that the reds are the reds are clumped together, blues are clumped together. The blues are the Democrats, reds are the Republicans. So this will be interesting to do with the Indian Parliament as well. But I guess in an Indian Parliament is even more monolithic. Everybody just votes along party lines, so it's not that interesting. But anyway, so this is what graphical models will give you. Another graphical model, which is actually a continuous graphical model, where each variable takes continuous real values. So this is where each node is a gene. So this goes back to that first example, where each node was a gene, and joint observations consist of experiments that you do, and each gene you have a certain measurement. And from these, you again need to learn a joint distribution amongst all of these genes. And a very interesting distribution, interesting because it's simple, is the Gaussian distribution. Just you have 10,000 variables. Let me just estimate a multivariate normal over these 10,000 variables. And even that is actually, you can interpret as a graphical model. And again, you can recover a graph structure from that. And here again, it's, yeah.
If node is common to two cliques, as in many of your examples, right?
A node is common, if they could, yeah.
Yeah, but then how do you factorize the probability?
So if you have multiple cliques, so you have a function just over the variables in those cliques, but the same variable could occur in multiple functions. Variable could occur in multiple functions.
Yeah, but then if the values are not consistent, then you should be getting zero. You want
Oh, so what you have is really, once you specify these functions, what this gives you is think of this as a function, and this is a product of these functions. So given the assignment of values to the variables, those would be the values that you would put in here. So
but only for consistency. I mean, XA and XP have to be consistent, right? Because they share, but...
Oh, right. So I'm saying that XA is really the configuration X restricted to the variables in A. So this is really notation. XA is really so if I have an assignment of 5 variables, and A is the first 3 variables.
So what I'm worried about is, for instance, each of those component things will not integrate to one necessarily.
Oh, right. Yeah. So there are issues.
The one you wouldn't get.
Oh, right. There are issues. So if so, that is an issue. So again, to reiterate, the consistency is not an issue in the sense that this is just notation that these are the configuration values restricted to variables in A. But there is an issue that if you have variables that are common to multiple cliques, then there is a normalization problem. So if XA, XB, XC don't share any variables, then normalizing P of X just amounts to normalizing these individual, it distributes, but otherwise it gets into a problem. And yeah, so that's why there is a huge cottage industry for how to deal with that. We won't go into that, but yes, that's a very good point. Right, so anyway, so this was just a very brief, much more of a ad, if you will, for graphical models. So we won't have time to get into graphical models at all. This is just to give you a flavor of things that people have been doing for dealing with high dimensional data. Okay? And I should mention that, again, graphical models have been used for 2 decades and more. And learning such graphical models from data, for instance, in the discrete case, this was this is actually an NP-hard problem. That given data, if you want to learn the best possible graphs, this is an NP-hard problem. And there were various heuristics and this and that, but it's only recently, using some of the techniques of high-dimensional statistics that we're going to look at, where we can actually guarantee, we can actually provide guarantees. You can provide a polynomial time method for which you can guarantee that you get the right thing with very high probability. So that's one way of finessing the NP-hardness problem. You have an NP-hard problem, which is difficult to solve, but you're going to solve something else that is going to be equal to the solution of the NP-hard problem with high probability. So it's a bit of a, so it's a great and exciting thing. Anyway, so this is what people have been looking at in the context of, yeah. How is the graphical model factorization captured? Right, so here, forget about this guy, this is just a normalization constant. If you look at this is just a summation over all the, so this is x transpose theta x. This is just a quadratic form. So theta, again, is a matrix. Again, I didn't go into any details because I didn't want to, but theta is really, think of these as weights over edges. So what you have here is a summation over edges, weights over edges, and a product of the expression values over the individual nodes. So it's really a sum over edges. And a sum inside an exponential is a product of functions over edges. So in this case, the cliques are the edges. Yeah. Anyway, so those were some examples of graphical models, which again have been very popular over the last couple of decades. But over the last decade, another class of models have become very popular, and those are what are known as structurally constrained models. And so many of you might have heard of compressed sensing, which has to deal with the structure of sparsity. And yesterday there were a couple of talks on low rank structure, and there was even one talk dealing with group sparsity, sometimes also known as block sparsity. So you have all these different classes of models, sparse, group sparse, low rank, and so on. The key overarching message in all of these is that you have a lot of variables, but so long as they are sparse, low rank, and so on, you can still estimate those with using very few samples. So that is the overarching message. So let's look at some examples. So is this better? Can people see the slides a little bit better? No? Okay. At least the figure is clear, is it? Hopefully, is that? Okay. So anyway, so let's look at the prototypical high-dimensional structurally constrained model, which is that of a sparse model. So here I have, this is just linear regression, really. Again, linear regression has been with us for 500 years. So the only twist here is that this is high-dimensional. So let's look at the linear regression model. I have an output y, and I have n observations, n responses, n samples of my univariate response y, and this response y is given as x theta plus w. So x is my measurement matrix, and theta is a signal that I care about. This is just the usual linear regression setting, and w is the noise. So theta star is what I want. So it's really linear regression because each response is given as a linear combination of my signal plus noise. Right? So what you observe is Y, you observe X. You don't know the noise, but you know its distribution. What you want is theta. So this linear regression and has been with us since the time of Gauss and so on. You can solve this using least squares, which is this expression in blue. If you assume W is Gaussian, this is just the Gaussian MLE. So Gauss of Gaussian, he just viewed this as a least squares problem without going into the statistical model estimation. So this is what people have been doing, but this works well if theta star is not too large. Yeah? So there is a lot of theory on the thing in blue. But if theta star is very, very large, so again theta star is this guy, and if the number of variables is much larger than the number of observations, then this is no longer a good thing to do because there are many, many possible theta star which might give you the same response Y. Right? Imagine that in the pathological example, you just have two observations, right? And you have this very long 1 million long theta star. Right? There are many, many possible signals which would give you the corresponding two real values in the response. So what do you do? And so a lot of people have had a lot to say about what to do, and that has really been this expression in red. What people have realized is that if the signal is sparse, by that I mean that if here you have 1 million long signal, but if only 10 of them are non-zero, everything else is zero, then I'm still in good shape. Right? Suppose I tell you that only the first 10 are non-zero, everything else is zero, then this is a simple problem. Right? This is no longer a 1 million long vector that you have to worry about. You only have to worry about a 10 long vector. Right? So you throw away all these other columns, like just chuck them away, and then you solve a least squares problem over 10 variables. The caveat here is that you don't know which 10 are relevant. So there is that bit of a slight problem. And what people have realized is that you can finish that problem. And you can finish that problem by regularization. So yesterday again there were a couple of talks on couple of different regularizations, but what people have realized is that for the case of sparse models, again sparse I mean that very few entries are non-zero, most of the guys are zero. L1 regularization, which is just a sum of the absolute values of my signal, this, if you add on to your MLE, will give you a sparse solution. By sparse, I mean that you solve this guy and your theta hat would have many entries which are zero, very few entries which are non-zero. And what's more, this is a tractable optimization problem because it's convex. Okay. And all of these papers, what they have done is that they have shown that this works under different settings. Okay. So this is the prototypical sparse models, and then you have block sparse models, which is just a matrix analog of the previous example. In the previous example, I just had one column of responses, one column of a signal. Here, imagine that I have, instead of just a single signal column, I have multiple signal columns. So I literally have a matrix, which is what I care about. And this is what I want to recover. And here again, if P is very large and M maybe not that large, but if now I have to essentially recover P times M parameters. So it's even worse than the previous case. Right? In the previous case, I just had to recover 1 million parameters. Now I have to recover 1 million times M. It's only worse. And what people have realized is that you can have a very simple extension of the previous thing, where in the previous thing, you just had a regularization which was a sum of absolute values of entries along a column. Here, what you do is you take the maximum along every row, and then you do a sum over rows. Okay. And this, again, is something that has worked. The other example, again, there was a talk not on this specific setting, but again on the low rank matrix recovery. Here again, your parameter, theta star, think of this as a signal, something that you want. Here is in the form of a matrix. And this matrix again is huge. Right? And in the previous case, what we said was that many entries in this matrix are 0, very few entries are non-zero. So that's a useful structure to have, domain knowledge, if you will. Here, you no longer have that thing, that structure. All of its entries are non-zero. But it can be factorized as a product of some thin matrices. And so here again, even though here you have k times m parameters, here the number of parameters are much fewer. Think of R as just 1, for instance. Then you have much fewer parameters, k plus m. So that's great. Right? And so here again, what people have realized is that you have your MLE, and so this people have known, given a statistical model, how to recover your parameter, or given a signal and certain measurements of your signal, how to recover the signal. We know how to solve this, provided that things are low dimensional. Here, people have just had a small addition to that existing knowledge, which is that you regularize your estimation problem. Okay, so let me mention a couple of words on regularization. Regularization also has been with us for a long time. Right? Depending on what you see, maybe in the 50s, it started in the 50s, Stikhanov and so on, but even before that, people have been looking at L2 regularization in some form or the other even before that. So regularization has been with us, and again, regularization came in solving inverse problems. I have a signal, right, theta star or whatnot. I have a signal, but I don't see the signal theta star. What I see is some measurement. So I have an indirect view of my signal, and from this indirect view, I have to recover the signal. Right? So people have had, so this is known as an inverse problem. Right? So the measurement is the forward, and then getting back the signal is an inverse problem. And people have been using regularization in inverse problems for one reason, and that is to stabilize your problem. Stability was something, again, I'll just give a very brief description, but if you're interested, I'd be glad to talk more. But stability is just this notion that if I change my measurement operator slightly or my signal slightly, right, I can resolve my inverse problem, I shouldn't get wildly different answers. Right? So this is especially true for scientists. Imagine that I have some genes, right, and I have a few measurements, and then I recover something, some graph structure connecting the genes. Right? And I do a few more experiments. I shouldn't get a wildly different graph. Right? So here, the pathological case would be no edge here shares an edge with the previous example. So this is something that's known as unstable inverse solution. And that scientists do not like at all, because they were quite happy with the thing that you just gave 10 days back. They gave you more experiments and then you gave a completely different answer. That's not good. And so people have been using regularization to stabilize the inverse problem. What regularization does is that it says, let's not look at the data. I know what's right. Right? So if you look at the regularization function, the expression in red, it doesn't involve the data at all. And so it stabilizes. It's more robust to noise in the data because it doesn't look at data. Okay? So you mix these two terms and it's stable. Over the last decade, regularization has served a dual purpose. In addition to stabilizing things, it also encourages structure. And so that's what's really exciting over some of these developments, again, which most of them have been in the last 5 years. So what people have shown is that in addition to stabilizing the solution, they also give you solutions, theta hat, which have structure. So here structure could be sparsity. I'll give you a solution where most of the entries are 0. I'll give you a solution which is low rank. Right? And yeah.
So I had a question. I read some result that some of these sparsity promoting regularizers that like L1 are not stable. Isn't that Is it true for lower models as well?
So again, people have, so that's why I don't want to go into stability so much. We'll talk more offline. So they are reasonably, they are more stable than unregularized problems, but you can always have more stability. So,
yeah, I think this was your paper, right?
Yeah, it's a different notion of stability. It's something called algorithmic stability, which is related somewhat, but a much, much harsher condition, and it's something that's used to prove generalization bounds. So it's not exactly.
Right. So yes. So one is that it's slightly different, and the other is that you can even for classical notions of stability make this more stable. And I'll be glad to talk more offline. Okay. So that was again just a high-level view of regularization. Okay. So can people read this? Barely.
Where I am.
No.
Still can't see very much.
Can't see. That's okay. I'll read them.
Maybe actually, yeah, but with your reading it. So
Okay. 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 So I will read out some key phrases. At least it'll help people concentrate on the thing. They'll just peer and concentrate on the slides, which is good, I guess. So here is a key question. What is the secret sauce? Really, that's the key point in this slide. What's the secret sauce behind all of this? So again, literally there have been hundreds of papers on these structurally constrained models, sparse, low rank, block sparse, whatnot. What's the secret sauce? So you have had regularization that you add to your MLE. But how do you come up with this regularization? Why does it work? Right? So these are questions that one might have, among many others. So here is the key answer. The key answer is that even though your signal is in a high dimensional space, whenever I say that it has some structure, I say what I'm really saying is that it lies in a low dimensional space. That's what I'm really saying. So if you look at the structure of sparsity, what I'm saying, if algebraically or analytically, what I'm really saying is that the structure of sparsity is really a collection of low-dimensional subspaces. And I'm saying that my parameter, my signal, is in a collection of some low-dimensional subspaces. I'm really saying it's in a low-dimensional subspace. I'm not going to tell you which low-dimensional subspace it is, but it's in a collection of these. And this is my domain knowledge. I'm going to say go figure it out, which low-dimensional subspace it is. And given that it's in a low-dimensional subspace, it shouldn't take us that many observations. Right? So that's really the secret sauce. Again, let's look at this line. Forget about the words. I guess it's lucky that you guys can't see, so that you can just concentrate on some key points. Yeah?
Really many of these low-dimensional subspaces, a lot of them.
Mm-hmm.
Right?
Yeah, it's a collection, right? Given a particular, so let me go with this example. That's a good point. So for the case of sparsity, right? So again, what do we mean by sparsity? I have a vector and very few entries are non-zero. Most of its entries are zero. So what is a subspace? Why is there a subspace? So let's say I have an index set S. Think of these as the entries in which the vector is non-zero. Right? Maybe the first 10 entries. Right? So let's say S is 1 to 10. Then look at the set of all vectors which are zero outside this index set. Or in other words, it support the entries in which it's non-zero is only within this index set. Now this is a subspace. And it's a low dimensional subspace because its dimension is only as is the size of S. So it's a low dimensional subspace if S is small. And if I'm going to say that a vector is sparse, I'm essentially saying that there is an index set and the vector lies in this low dimensional subspace. And what Gilad mentioned was that what I really have is a collection of subspaces because I'm not telling you which index set is relevant. Right?
You choose S, right?
Right. So depending on further information, there are multiple index sets. And so that really is what the regularization does. It searches through these index sets. But if I tell you which index set, now you have a very, very simple problem because it's a low-dimensional subspace. Again, if you think back to sparse estimation, I have 1 million parameters. If I tell you that only the first 10 are relevant, you have a 10-dimensional problem. You don't have a 1 million dimensional problem. So it's really become a search over subspaces. But given the subspace, estimation is simple. Okay, and let's skip the groups, structured group structure. Let's look at low rank structure. Again, this is the thing. Again, in a low rank matrix, I can have a really big matrix, m by k, right? M times k parameters. But if I'm going to say that it's low rank, rank r, right? Again, there is a low dimensional subspace that's operative, and here is the low dimensional subspace. If you specify the row space and the column space, I can only look at those matrices whose row space is within the specified row space, column space is within the specified column space. Now if you tell me the row and column spaces, again each of which have rank at most r, dimension at most r, then its dimension, now this again is a subspace, and its dimension is at most r, as in it's small. And here again I have a collection of subspaces. As I change my row and column space, I get different subspaces, and really the goal is then to pin down which of these subspaces are operative. But yeah.
So how is the second one incorporated into the optimization? The first one, sparsity, is very easy to regularize, right?
So it's great that you think it's, even if in the first case it's not that obvious how to go from this to the regularization, right? Yes. So I'm going to come to that, right? So so the question was, okay, so it's great that the parameter lies in a low dimensional subspace or a collection of low dimensional subspaces. So intuitively I know that the problem is at least somewhat simpler. When I say that it's sparse, it's this, so it's somewhat simpler. How do I use this? And that's where we're going to go to next. Okay, so let's look at the problem formally. What I have is a set of probability distributions. So whenever somebody says, oh, I have a statistical model, what they're saying is that they have a family of probability distributions. It's a family in the sense that it's really a set of probability distributions indexed by something. Here it's indexed by theta, which is a parameter of interest. Okay, so that's the setting. I literally have a sequence or a set of distributions indexed by this theta. Now I have samples, n samples, z1 to zn, and all of these samples are coming from one of these distributions. If you think back to the linear regression model, right? So again, you have different linear regression models indexed by your coefficient vector theta star. Right? Think back to the Gaussian graphical model, indexed by your covariance matrix or inverse covariance matrix theta star. You have different Gaussian multivariate normal distributions. Right? So given theta, you know the distribution, but and there is one true theta star to rule them all, and you don't know that. What you do know is observations from this distribution. So the question, the inverse problem that you have to ask, and people have been asking for hundreds of years, is how do you recover the signal given that what you're viewing is really an indirect view of the signal, just these observations, z1 to zn. And what we have been seeing, the gestalt of all those previous faint slides was this. Theta hat is my estimate, and I'm going to get that by solving an optimization problem. And the optimization problem is a sum of two components. One is a loss, which is really the goodness of fit of my signal to the data, and the other is a regularization. And so I have these two components, and so this people know how to get, right? It's just a goodness of fit of a signal to the data that comes from your noise distribution and so on and so forth. statistics over the last 100 years, 50 years, we know how to do this. The second component, that's where the progress over the last decade has been. Given the subspaces, how do I come up with this R theta?
Yeah, so you said that the regularization term is independent of the data, but instead of searching through all the subspaces, can't you use the data to actually get some idea of where this lies, some subset of those subspaces?
So
instead of going through everything.
That's a good point, which is that can we use the data to tell us which subspace? In a sense, that's what this is doing. So I'm adding this to my objective, and the objective also involves data. So there is one term involving the data, which really, so if you think of these as two competing parties, one party says that I'm going to fit the data, and the other party says that I'm going to fit the structure. And both of them, the tussle between them, what is the optimal trade-off, is done by solving this optimization problem. Okay, so let's see how do we pick this out of data. So here is we'll have a little bit more to say, but here's a one slide in case we don't get to all the gory details. So so again, this is a very analytical view of a good regularization. And again, I guess, can folks see this? This is the key line. What we call decomposable regularization functions. Again, a regularization function, think of this as, say, some norm, okay, that satisfies a triangle inequality. Now, if I apply this regularization to a sum of two terms, okay, so here U and U perp are really suggestive, but just imagine that they are two separate signals, and I apply my regularization function to the sum of these. If it's a norm by the triangle inequality, this side is less than the sum of these two, right? So R of A plus B is less than or equal to R of A plus R of B. You have that for any norm, right? Any regularization function which is a norm is going to satisfy that. But a regularization function that is good for your structure won't be an inequality, but will be an equality for certain vectors. So suppose I have these subspaces, right? Say for the case of sparsity, I have a collection of subspaces. Suppose I have a vector which is in a subspace, and I have another vector which is in an orthogonal subspace, right? So that's what U and U perp are. So U, again, think of this as a vector with structure, okay? And U perp is a perturbation away from the vector with structure, okay? So since it lies in the low dimensional subspace, it's a vector with structure. U is a good guy. U perp is a bad guy, right? Because it's in a subspace orthogonal to that. Now, if I apply my regularization function to the sum of these two, it's not less than or equal to, but it's exactly equal. So it's the maximum possible it can be, right? It really hates. So think of regularization as a cost, right? So if your signal is bad, this function will be large, right? And so here what it does is that since it does not like this U perp at all, and this regularization function applied to the sum is the maximum possible, okay? And so again, this is a very abstract view of what a good regularization function is. But really, this is what we need. You give me any function, if it satisfies this, we have theorems which will tell you that they will perform excellently. So this is an implicit characterization rather than explicit. And if you have time, we will get to the explicit characterization as well. Just to give an example, this again was a subspace for the case of sparse structure, right? So in the case of sparse structure, I have an index set, and given that index set, the set of vectors which are 0 for coordinates outside the index set, this was my subspace. Now if I look at this subspace, take a vector in this subspace, call that alpha S, right? It's 0 outside the index set. So its orthogonal subspace will consist of vectors which are 0 in this index set, right? So that's what I have. So if I add these two guys up, which I call alpha S and beta S complement, the sum of their L1 norms, the L1 norm of their sum is the sum of their L1 norms. So that's what we mean by decomposable. So the L1 norm is decomposable with respect to the sparse subspaces, the sparsity structure. And this is what we need to show that the L1 norm will give us good results. So this is a good trick to see if you just think of a new regularization, whether it satisfies this or not. Now let's think back to the notion of what we know of as structure. So given the structure of sparsity, we said that it was really a low-dimensional subspace, but a collection of those. Low-dimensional subspace here, low-dimensional subspace there, and so on and so forth. A collection of low-dimensional subspaces. Now, when I say that something is low-dimensional, another way of thinking of that is that I have a set of, look at its basis elements. Right? Since it's a subspace, I can look at a set of basis elements. Again, a basis is just a set of vectors. So I said any vector in the subspace can be written as a linear combination of these basis elements. Right? So when I say that it's a low-dimensional subspace, the set of basis elements, the size of the minimal basis is very small. I need very few elements so that their linear span is the entire subspace. So Chandrasekharan and folks at MIT, they refined, so again this notion of structure as a collection of subspaces, it was Sahand, Negaban, Martin Wainwright, Ben Yu, and myself. So we had a paper. And so this other paper in terms of basis elements was by Venkat Chandrasekharan, Ben Recht, Pablo Parillo, and Alan Wilsky. Okay. So they refined this notion of subspaces into basis elements, what they call atoms. And in some sense, it's actually an easier way of thinking of things. You don't need to think about subspaces. Right? You just need to think of basis elements. And now, instead of worrying about a collection of subspaces, I just need to worry about a collection of atoms. Okay? So let's look at an example. So let's look at the case of sparsity. Right? So can folks see the diagram here? Yes? Okay. So in the case of sparsity, I have a vector which, so imagine this is 1 million long, but only 3 entries are non-zero. Right? So I have a vector which is sparse, right? 3 entries non-zero, million minus 3 is 0. So one way of writing this million long vector is a sum of 3 vectors. And these 3 vectors are 1 in only 1 coordinate, 0 everywhere else. You can think of these as the basis elements of the sparse structure subspaces. Right? So in other words, I'm going to say that a vector is sparse if I can write it down as a sum of a few sparse basis elements. And in this case, the sparse basis elements are just the coordinate vectors. 1 in 1 entry, 0 everywhere else. Right? It's almost a tautology. Right? If you give me coordinate vectors, you take a linear combination of a few coordinate vectors, you're going to get a sparse vector. Right? It's a very simple structure. Similarly, if you look at low rank, if I have a matrix that's low rank, take a sum of a few one-rank matrices. If you take a sum of 10 one-rank matrices, your rank is going to be at most 10. Right? And so even if you have a zillion parameters, just the simple notion of atoms tells you that this matrix, if I just tell you that it's a sum of, say, 2 one-rank matrices, you know that this matrix has low-rank structure. And so that is really what the basis element view, the atomic view, gives you. That it's a sum of a few simple components. Yeah.
What is the notion of an atom? Just the basis element?
Just the basis element of those subspaces. But I can really come up with my own set of atoms. Right? So my idiosyncratic set of atoms, I just say these are the vectors I care about, and these are my atoms. And you can say that with respect to my own crafted set of basis elements, because again, let's say everything is an R to the P, right? So I can come up with any set of vectors and look at the linear span, and that gives me a subspace.
So why does it make the problem to be simpler? Because I mean, you still have an exponential space from which you have to pick those small numbers. So I guess I'm not able to visualize why does it make
So so there is a search problem. So again, this goes back to the collection of subspaces as well. If you tell me exactly which atoms are operative, then things become simple. If you tell me exactly which subspace is operative, then things become simple. Here there's a search problem in the sense that I have to search which subspace to pick, and there is that problem. But we know how to solve that, but at least this makes the problem less horrendous. Right? At least it's a collection of subspaces, at least it's a collection of atoms. And it's now a much simpler problem in the sense of searching for which set of small atoms I have to pick.
But you're still searching through an exponentially large space.
You're searching through a large space, yes. And you have to have a way of finessing that. And that is what we get through regularization. Do we get an equivalence between subspaces? Right. Atoms? Yeah, definitely. Because let's look at the collection of subspaces. It's a collection of low-dimensional subspaces. So each of those has a set of atoms, a set of basis elements. And you just take all of them together. Just take the union over your collection of all the basis elements, and that gives you the set of atoms.
So I was just trying to see what is that called? Instead of searching over subsets, you're searching over the.
So what is this bias? So there were two problems involved in this. One was that if earlier we had a very amorphous view of what structure was. If I tell you that something was sparse, it was very difficult. Or if I told you something was low rank and so on. For each such structure, you had to come up with your own search procedure. Right? And you had a very amorphous view of what it really meant, how to craft your search procedure. Here, it's a very abstract view. I just have atoms, right, in R to the P, and what I'm given is a collection of atoms, and I have to search through linear combinations, small linear combinations of these sets of atoms. How to do that is still outstanding. I have 2 minutes for that, but at least this makes the problem formalizes the problem and generalizes the problem. So that it's common to all of these different sparse, low ranks, and so on and so forth.
I think it's also the fact that you're explicitly sort of introducing sparsity structure you want to encrypt, right? I mean, you sort of decide at the outset whether it's sparsity or which one of these.
Right, right. So there is that, but it's still abstract in the sense that so if I'm going to tell you how to craft regularization functions with respect to a set of atoms, then if I can do that in an atom agnostic way, then it's great, right? So now you can come up with your own structure, and then you have a way to craft regularization functions, analyze it, and so on and so forth. So that's the advance. It's a unified framework for looking at such structurally constrained models.
So is there an example of a new, say, structure that you can discover with your unified framework which was not known before?
Oh, definitely. So I won't have time to get into that. I'll be glad to look at offline. So a lot of these things are what I call homogeneous component-based models. So these are what I call component-based models. Do I have it on the next slide? Okay. So the other thing is that even graphical models you can write in this framework. Right? So even graphical models are really component-based models. But let me skip that for now. What I want to note is that all the things that I have mentioned are really what I call homogeneous models, because all the atoms, basis elements, have a single type of structure. Right? But what if I take atoms corresponding to sparse structures and take atoms corresponding to low rank structure, throw all of them in, mix them up, and then ask for a simple structured parameter. So that is something that people have been looking at, but there wasn't a unified framework for that. So literally, this is what you could do. You could take all these atoms corresponding to different structures, take all of them, mix them all up, and then you get a new regularization, which wasn't there before. So that is also something that it'll get to you. So I guess that's what I call a heterogeneous component-based model. And there are a few papers, but again, we can analyze that in a unified way. So let me stop here though, because we won't have time to go into that. Thanks. Okay, sure.
Are there any more questions?
We talked about inference being NP-hard for model and inference we can talk about approximate.
Right.
Approximate
Right. So it was right. Right. So the way in which we got around that is that to phrase the graphical model inference problem as a sparse estimation problem. So if you think back to a graphical model parameter, I have a graph and I have weights over edges. Right? So let's say I have m edges, I have m real values. Right? Now imagine that I have a complete graph and I have weights over all the edges. So p nodes, p choose 2 possible edges. Imagine that I have a vector in r to the p choose 2. But many of these entries in this vector are 0. Right? Because if I don't have an edge, that weight is definitely 0. So we can do this reduction of a graphical model inference problem to a sparse estimation problem. Now sparse estimation is still NP hard because, as many pointed out, I still have a search problem. I have to search through these subspaces. So there's still that issue, but you can still finesse that using regularization. And so that is the way we finesse it. That searching through the subspaces, again, another key takeaway is NP hard. To do that exactly is NP hard, but since we are dealing with data anyway, I don't need an exact solution. I can just get somewhere else that I can go tractably, and that turns out to have good enough statistically. And so that's how we finesse the NP hard problem. So in any of these, sparse estimation, low rank estimation, I have an underlying signal in mind, and I know that it has certain structure. So I can recover that structure in polynomial time. Even though that involves a search, which is NP hard to do exactly, I can still recover that in polynomial time under certain conditions by solving a different problem. Right, so as we're saying, graphical model inference problem, I can reduce that to a sparse estimation problem. Sparsity constrained estimation problem. It's not a linear regression problem, but it's not that much more complicated. I still have a vector of parameters, many of which are 0. That's. Oh, we don't. Oh, so right. Okay. So right. Yeah, I see your confusion. Right. So when he was saying graphical model inference, he meant learning a graphical model, and you were talking about inference on graphical models.
So what you're essentially saying is that any of the structure learning algorithms that are there in the graphical models you can actually derive from this framework. Because
right.
Imagine like you have a fully connected graph, and then you are dropping those edges, like you said, using this parsing. Can you do something like that?
So there were methods that people were using, but they were largely heuristic. So they weren't. You can't get statistical guarantees for them. But if you reduce it to a sparse estimation problem, then you can get methods that are polynomial and come with statistical guarantees. Now, the thing that you were specifically mentioning, which is that adding and deleting edges. So even for sparsity constrained problems, even though I've been talking a lot about regularization, you also have greedy methods. And I can point you to some references that I have on greedy methods which work for graphical models.
You answered his question. You said that your theory actually suggested a new model of combining sparsity and low rank. But the already existing model...
No. So I meant to say that is one way in which you can get a new regularization, but I didn't mean to say that that's not been done. So sparse plus low rank is there. Then in fact I have in the slides I have some examples on sparse plus block sparse and so on and so forth. So But what about sparse plus block sparse plus low rank plus something else? That doesn't exist, right? So that is what I meant. That you
I'm
can.
curious to see it after.
Sure.
Thank you.
Sure.
Thank you very much.
Sure.